Okay, welcome back everybody. This is ELNC 1533. This will be the first in a series of videos, I hope. We're still covering Unit 3 material here. And what I'm going to start with is looking at how to determine the waveforms for a 6-pulse 3-phase rectifier. So behind me, you should be seeing the rectifier and the line-to-line voltage diagram, and then below that we're going to solve out what the individual currents look like as well. Okay, so starting with line VAB, the first letter tells you which device is going to conduct in the positive half cycle, and the second letter, in this case B, tells you which device on the negative leg is going to return the current to the AC system. So I'm just going to circle the two devices of interest here. So we've got Q1, which is your phase A positive device, and we're coming back on phase B, so that's Q6. So those are the two devices that are conducting. When Q1 first becomes forward biased, doesn't happen at the zero cross of the line-to-line voltage VAB, but rather 60 degrees in. So alpha 0, I'm just going to highlight that for you right down here, happens at this point on VAB, which is 60 degrees in on line VAB. But let's say that we gate at 30 degrees. What is that going to look like for a waveform? So let me grab a green highlight here, and I'm going to start up right at this point here. So that's 30 degrees on line VAB. Now I know that each of these devices is going to conduct on a 6-pulse rectifier for 60 degrees, and each one by itself. So looking at Q1, so we're firing Q1, is going to conduct initially for 60 degrees, and then we're going to turn on a different SCR in the negative half leg. So you're going to see another transition at 60 degrees, but each device by itself conducts for 120 degrees. But let's just follow line VAB. So for this moment in time here, we have Q1 and Q6 working together. Okay, but what happens at 60 degrees in at this point, which is now at 90 degrees as far as alpha is concerned? Here we have to fire phase A SCR again, which is Q1 on the positive leg. So we switch up here, and this time current is going to return through Q2. So I'm just going to grab a different color marker to show that on the second part of the conduction, Q1 is still conducting all the time, but on the second part of Q1's conduction, the current commutates off of Q6 and then on to Q2. So if I highlight that, you get this waveform. That represents there the full 120 degree conduction for Q1. So Q1, I'm just going to draw a line here. So Q1 is conducting in this period of time right here. And if you look at Q6 was on in this period of time, and presumably before that as well. So then the rest of the time, Q2 is going to pick it up. So Q2 is going to be in here. And if you look at the next part, or the next line-to-line voltage that's going to be conducting, you see the letter C in the second case out to here as well. So having drawn 120 degrees of conduction waveform for Q1, we can assume, as long as you haven't changed the firing angle, that the waveform is going to continue along that pattern for the rest of the cycle. So the rest of the cycle then is going to look like this. And let me just make a note of the fact that this is with alpha equal to 30 degrees. So that's the resulting DC waveform you're going to get with alpha equals 30 degrees. I'm also going to draw what the currents would look like down in the bottom. So if we look at Q1, yeah, I'll stick with blue. So if we're looking at Q1, Q1 turned on right here. And it stays on until this point here. So SCR Q1 is conducting in there. And you may get a test question like this. So the thing is, you look for wherever the first letter is on the waveform. Once you've got the timing in place, the first letter tells you which device is conducting in the positive half cycle. The second letter tells you which device is conducting in the negative half cycle. So I know that I'm going to be off now for at least 240 degrees. So you're on for 4 divisions, and each division is 30 degrees. So this is going to be off here, then it's going to be off here, and then it's going to come on again there. Now what about Q2? Q2 is the return path in the second half. So we know that Q2 was going to be picking up the ball here and put it on for 2 more cycles. So it's going to look like this. And then it's going to be off for 4 divisions. So we wouldn't see it coming in anymore within the time constraint of this chart. Q3 is the next one to pick up the ball after Q1. So it's going to look like this and be off the rest of the time there. And carry on like that. I'm going to jump down to Q5 because that one's easier for me. So Q5 will pick up the ball after Q3, which is the phase CS here. And move over a bit. I know it would be on at this point here as well. So that draws that one out. Okay, so coming back to Q4. Q4 is phase A. So what I'm looking for in the waveforms is where the letter A becomes the second letter. And that happens right at this point here. So I come down, so I know it's going to be on there. And it's going to be on for 120 degrees again. So I can draw it out like that. And it'll be off for 4 in front, and it'll be off for another 4 before that. So we don't see it anymore within this picture. And now I come to Q6. So we know that Q6 was on at this point for phase A. So it was on here. And then it'll be off for 4 more. So that's 1, 2, 1 more. And then it'll be on the rest of this time here. Now, if you're wondering, why do we sequence the labeling here in this picture? So if you look at the schematic, you'll see that the top 3 SCRs are Q1, Q3, Q5, and then the bottom devices, Q4, Q6, Q2. And it seems like kind of a weird sequence, but look at our timing chart. So I've put them in order of Q1, Q2, Q3, and so forth. But if you look at the waveforms, you can see them all moving in the same direction. So that shows you that the actual sequence in which those devices commutate from one to the next actually occurs in the numbering order. So even though it seems a little bit random in the schematic, the number actually represents the sequence of turn on. Okay, so those are the devices for a 30-degree angle. If you're firing at a different angle, you're just sort of shifting all that stuff around. But what about phase A? What does the actual line current look like on phase A? So I'm just going to go to a different color here so we can show that line current. Now let's go with red. All right, so Q1 and Q4 are both connected to phase A. So Q1 represents the positive half cycle. So what I do is I pull down Q1's waveform. And this is what the current's going to look like on the AC line for the positive half cycle. And now I got to find its negative match. So when current flows the other way through phase A, it's going to come back on Q4. So looking at Q4, that I'm going to draw now as a negative current because that means it's going the opposite direction in line A from what the current was when it was going through Q1. Okay, so the red line now represents what the AC line current is going to look like. And I should note for you that the current going through the DC here is basically flat. So if you look at the current ID as a function of time, then you basically have a flat current. And so what we're assuming is that the inductance is large enough to filter out the AC ripple. And you guys should know at this point in time that if you look at this waveform, we have 1, 2, 3, 4, 5, 6 symmetric pulses that are happening in each cycle. So the AC ripple frequency across the DC load is actually 6 times 60 hertz or 360 hertz. So the fundamental ripple frequency again is 360 hertz at the load, even though the AC line frequency is 60 hertz. Okay, let's switch it up a bit and let's look at some different angles. So I'm going to take the same thing and I'm going to just erase everything I've done here. All right, let me pull up my green marker again. Well, just a second, guys. I got a dog in here. Bella, go on. Okay, here's my green marker. Last time we looked at 30 degrees. Let's look at 60 degrees. So I pick off 60 degree point on VAB. I know I'm going to go for 60 more degrees before I fire the next pair. Still using Q1 on the positive. So basically what I've just highlighted for you right now, that's with Q1 being the positive feed. Halfway through it comes back on phase B, and then on the second half of that time it comes back on phase C. So just to show you, so for the first part, current's coming around this way, coming back on phase B. That's the first part. Let me change the highlight color and then I can show you what the path. So for this second part right here, the current is still going to come through Q1, but this time it's going to come back on Q2. Okay, so for both parts of that, we're using Q1, but 60 degrees in, the ball transfers over from Q6 onto Q2. And that you can work out based on the current waveforms we had before for each of the other devices as well. All right, so let me carry on with the rest of the waveforms. So for 60 degrees, your waveform is going to look like that. Now, what does the average DC voltage do? Well, the average sort of comes down the middle of that. So your average DC voltage is going to be sitting in around there somewhere, probably a little bit lower than that. So this is your VDC. And if you look in the Wildy textbook, you're going to see that the formula for that is 1.35 times the V line to line voltage times the cosine of your firing angle. Okay? And we're going to do some work problems using that formula a little bit later on. So anyways, that represents the case for 60 degrees, right? Okay, we've done 30 degrees, 60 degrees. How about, well, let's look at the special case of 90 degrees. So again, coming down to 90 degrees, I end up with a waveform like this, goes 60 degrees, switch up, and I just keep painting that pattern all the way through. And this time, you notice something. Your average is a line right down the middle. So basically, you have as much time above the zero axis as you have below the zero axis. So the net result at 90 degree firing angle is you have a 0 voltage overall. So you're never going to get any current going through, say, an inductive field at 90 degrees because you've got as much voltage above the zero as you have below it, and they just cancel out over the cycle. You can see that from the formula too, because if your DC voltage is equal to 1.35 times V line to line times the cos of 90 degrees, well, the cos of 90 is 0, so it doesn't matter what your line to line voltage is, you're just going to end up with a net 0 voltage. Now what happens when we go past 90? So now let's pick off 120. So follow my VAB all the way down to 120 and then continue on that line-to-line voltage and just keep painting that off like that. You can backtrack that and that's your waveform. So the entire time you're firing at 120 degrees, your average voltage is now less than 0. In other words, it's negative. So how can I have a negative voltage? Well, if you have a highly inductive load like I'm showing here in this picture, at some point in time, let's say your current's coming around like this, and we'll just say that at this moment in time it's coming back on phase B. SCRs have to be forward biased to keep conducting. So obviously the polarity on the SCRs is going to be like that, otherwise they would be shutting off. If current is going in this direction, then you would have to have positive and negative across your resistor to respond in that way to the current, right? Resistors are just pure loads which don't have any phase shift associated with them. So current always flows into the positive terminal of a passive load like a resistor. But what's going on with the inductor? Well, the inductor is going to have a different polarity. Its polarity is going to be doing that. Why did the polarity on the inductor flip? What's happening is that the inductor has this magnetic field stored across it. And when you start going negative on the rectifier, so we actually have a net negative, sorry, I'm doing this wrong. Okay, so my VDC or my EDC, so let me just draw this down here. So EDC is the voltage here and here. And according to the waveform, that's actually positive here and negative there. In other words, the total volt drop across the inductor and resistor is in the same polarity as the volt drop across the inductor. It's backwards, it's negative. And that's all being contributed to by the inductor. So as I was saying, you got this magnetic field stored in that inductor, but now because the net DC voltage on that circuit is negative, the current can't maintain a forward direction through the inductor. It's actually collapsing. And because the current is collapsing, the inductor is responding with a reversed voltage that tries to keep the current going. So the inductor is acting like a source during this time. This is what we call inversion. So collapsing inductive energy is the only thing that's keeping this going. Once the current through the inductor collapses below the minimum hold level of the SCRs, then the SCRs are just going to shut off. And at some point you would see the voltage waveform kind of doing this, and then at some point it'll just go to 0. Okay? So even if you maintain the gating in a past 90 degrees, you're just going to end up with 0 current at some point in time. So again, the inductor is what's providing a temporary energy source to maintain forward conduction. So irrespective of whatever the AC voltage is at that moment, the inductive volt drop is negative enough to keep the net polarity on the SCRs forward biased until such time as the current collapses to 0. Okay? All right, let's do some other stuff. Now, you could keep doing that with other angles. I'll leave that with you as an exercise, including filling in the chart for finding the currents at the various firing angles. But I'm going to switch us over to a different type of circuit. This is the semiconverter. So things are a little bit different with the semiconverter because you're controlling the SCR gating on the top 3 devices, Q1, Q3, Q5, but the bottom diodes just commutate as soon as they're forward biased. So for example, if phase B is the most negative phase, and it will be when we look at our chart initially, then D6 is going to be the diode that's turned on. All of the diodes share the same anode, so the only diode that's conducting is the diode with the most negative cathode. All right? So let's look at 30-degree firing angle. At 30-degree firing angle, we start off with VAB, but I stop right at another 30 degrees later. You know what? I'm just going to narrow that down so it's a little bit less stick out-ish. Is that a word, stick out-ish? I don't think so. Okay, so there's my first little bit. Now I am touching the place where the phase C diode actually becomes the most negative, more so than phase B. So we were coming back, so initially current was going around this way and then was coming back this way. But now we are at the junction where phase C becomes more negative than phase B. So without having to gate anything, D2 is going to be the most forward biased diode. So D6 just commutates off naturally. That means for the rest of this time, the current's going to follow this way. Okay? Now I'm going to end up firing phase B SCR, which is Q3. So now it's going to step back up and we get the same pattern going on here. Okay, so if that's not coming through for you dark enough, I'm just going to kind of put another line through there. That might be easier to see the overall profile. Okay, so that's what your waveform is going to look like at 60 degrees. 30 degrees. So this is alpha equals 30 degrees. Okay, let's try it at 60 degrees and see what happens. So now I'm going to wait till 60. So here I'm following this, but now I never actually end up on any other diode than C. So the whole time I'm firing at 60 degrees, phase C is the only device that's going to be negative until such time as I follow up with, sorry, I drew that wrong. Okay, here's what it's going to look like. So I'm going to follow V, A, and C because C is already the most negative. So VAC is the voltage I'm following, and I haven't fired B yet, so I'm just going to carry on with that for the full 120 degrees. And then I switch up once I get to 1, 2, 3, 4. So that's 60 to 1. Yeah, so there's my 120 degrees. So now I'm going to fire phase B, and it's going to follow up like that and like that. Okay, so that's alpha 60 degrees. Okay, let's try going back a little bit further. Let's try 90 degrees and see what we get. Now at 90, I'm going to be following VAB, then I see that VAC takes over, so right here is where I turn on. Okay, so I'm going to follow that all the way through for 120 degrees. And then I switch up to here, and I switch up to there, so I do that. But that's not technically correct. And here's why. If you look at these regions here, so let me grab this other pen. So right now you see this negative voltage here, this negative voltage here, and this negative voltage there. It turns out that a semi-converter, which is 3 SCRs and 3 diodes in the return path, can't actually produce a negative voltage across the load. And that's because as soon as I get to this point right here, at this point, we notice that the diode that is most negative becomes the phase A diode. That means D4. So D4, at this point, D4 is on, but Q1 is still on. So Q1 is on in this region here. So if Q1 and D4 share that last little piece where the voltage is wanting to go negative, and they're both working together, that means that the current at that point in time would be freewheeling through these two, and no current is going to be drawing from the line. So that means my waveform will actually go flat at that point. So it's going to look like this. So the moment the voltage tries to go to 0, it won't, because it's during that period of time that you're actually freewheeling with the device opposite the SCR that you've turned on. Okay? So unlike a full wave bridge, the converter cannot produce negative output voltages. And you might think, well, is that a problem if it's a rectifier? It is a problem for some things like SCR controllers used on rectifiers for main motors or synchronous motors. If you're trying to get the current down quickly, it's useful to have the capability of inverting or having negative voltage, because it allows you to force the field down faster. So it gives you better time control over the excitation if you're trying to regulate the volts or the VARs or something else on the AC system. Okay, so now let's look at going back further. Let's phase back to 120 and see what that comes off looking like. So 120 degrees means I'm first turning on Q1 here. And now I've only gone 60 degrees. I still have to go another 120. So you'll notice that the waveform is really starting to come down faster here. Okay? So this is basically what your output voltage is going to look like. It's going to be a bunch of little spikes. Now the other thing I want to point out to you is we've got 1, 2, 3, and then we start all over again. Okay, so you got 3 pulses per cycle. So that means you've got 3 times 60 hertz equals 180 hertz ripple, and that's what you're putting across the DC output. So the DC output, as far as a ripple frequency is concerned, is seeing a current, or a voltage rather, with 3 symmetric pulses per cycle. So it's seeing a fundamental ripple frequency of 180 hertz in addition to the DC level. So the DC voltage will probably be around here somewhere. So this is your VDC. And there's a different formula for that one than there is for the full wave 6-pulse rectifier. And we'll look at that one a little bit later on as well. Okay, so you should be able to solve it for the rest of the angles as well, but that's basically how we're doing it. And we'll end this session right now, and hopefully I'll get some more videos up to you guys shortly. All right, thank you. Take care.